So we have discussed about the first law of thermodynamics for a closed system in the last class, and today we are going to discuss about the open system and first law of thermodynamics. That means how we are going to apply the first law of thermodynamics for an open system. So first of all, we will discuss about what is the open system. Open system is one in which both energy and mass cross system boundary. So this is an open system which is shown here. We have discussed about it. This is the inlet to the open system. This is the exit of the open system. So the mass is leaving here. Here the mass is entering actually. This is the control surface, also called the boundary, and whatever is there inside the control surface is actually control volume. And we already know that in case of open system, both energy and mass cross the system boundary. Now we should know what are the various examples of an open system. Now the examples of open systems are steam turbines or gas turbines, compressors, nozzle, diffuser, heat exchanger. So the question is how to apply first law of thermodynamics to an open system. Before we talk about open system, we should know what is the steady state, and let me give you about its example also. Now what is steady state? When properties do not vary with respect to time, then it is known as steady state. For example, if velocity at a particular location in a system is 5 meter per second square, 5 meter per second, and does not vary with time, then the system is said to be in the steady state. Rather, we should consider all locations of the system, and if properties are not changing, then it is known as steady state. Now, let us see what is the meaning of the steady state. For example, I have a particular thermodynamic system, and if I am considering here, and the velocity of the fluid at this location is, let us say, 5 meter per second. So, and this velocity is at a time, let us say, 2:05 p.m. Now, let us say if I take another time to 5.10. So this 10 depicts the time period which is actually equivalent to 10 seconds which have elapsed after the 2 hours and 5 minutes actually. So if now also if the velocity at this particular location is 5 meter per second, then I will say that it is the steady flow. Or if I take some other time, say 2 5 and 30 seconds, okay, and at this moment also for all these movements the velocity is 5 meter per second at this particular location, then I will say it is a sort of steady flow. But it is not necessary that the velocity at this particular location is also 5 meter per second square, 5 meter per second. Let us say if the velocity here is 6 meter per second, and with time these times only it is 6 here, at this time also it is 6 here, at this time also it is 6 here. That means here also there is steadiness in the velocity. So steadiness means the velocity properties do not vary with respect to time. So there is one more thing that we should know about the steady state. In steady state, heat transfer rates and work transfer rates also remain constant with the time. So in totality or nutshell, we can say d by dt of any property is equal to 0. That means if we are talking about dv by dt, now dv by dt shows the rate of change of velocity with respect to time, and if this value is 0, it means velocity is constant with respect to time. Okay, so this means the property velocity is not varying with respect to time and hence it is steady. Simultaneously, here we have shown QCV, it does not change with respect to time, and WCV, it also does not change with respect to time. Why we are putting this CV? CV means work which is going into the control volume as per the direction of the work shown in this particular diagram. Similarly, here this is QCV means the work which is the heat transfer which is entering the control volume. Moreover, I would like to tell you when these are not work and heat transfer are not changing with respect to time, it means if this heat which is entering to into the control volume is 5 kilowatt at any moment, this will remain constant over the period of time. That means if it is 12 hours and 12:10 or 12:15 or 12:20 hours, the value of QC will remain constant, and same thing will be the work also. Suppose the value of this work is 10 kilowatt. So with time, this value will also not change, and the system will be in the uh, steady state. Next thing is the steady flow. Actually, now what is the meaning of the steady flow? Now, steady flow is very simple. Steady flow means mass of the fluid per unit time. So we are basically talking about the mass flow rate. Actually, m dot has a unit kg per second. So it is mass flow rate which is entering some control volume is equal to the mass of the fluid per unit time which is leaving the control volume. Then such a flow is known as steady flow. It is very simple. For example, if I have a control volume here, this is the control volume which I am considering here, and let us say the mass which is entering is 5 kgs per second, and the mass which is leaving is also 5 kgs per second. So I say this is a steady flow condition. So in steady flow, I say that this is the mass which is entering denoted by subscript I, and the mass which is leaving is shown by ME. E stands for which is exiting or leaving the system or the control volume. So I say for steady flow, Mi dot is equal to Me dot, and I can say that it is equal to M dot because the value is same whether it is entering or leaving. So I stands for entering, E stands for exit. So mass entering is equal to mass leaving in case of steady flow. Now we can apply the first law of thermodynamics for an open system. Now let us first of all consider an open system. Now you can see it here. Here we have considered a datum. Datum is same for both inlet and outlet. So I can say that this is datum. Okay. And this is the thermodynamic system. Which system? It is an open system because what you can see here, we have a inlet here, we have a outlet here. Okay. So in the inlet, what is entering? It is the Mi. This is the mass flow rate of the fluid which is entering. This fluid has a internal energy Ui. It has a velocity Vi. It has a specific volume small vi, its pressure is pi, and the temperature is Ti, and its elevation with respect to the datum is Zi. And similarly, the mass which is leaving the control volume is Me, its internal energy is Ue, velocity is Ve, specific volume is small ve, pressure is Pe, and the temperature is Te. And you can see we also have considered the value of heat transfer which is taking place into the control volume, and we have this work transfer which is coming out of the control volume. So we have shown the energy interactions which is taking place across this control volume, and we have also considered the various properties of the fluid and the mass flow rate of the fluid also. Now, what is actually first law of thermodynamics for an open system? Now, first law of thermodynamics for an open system is mere energy conservation principle. That is, energy entering into the control volume is same as the energy which is leaving the control volume. So we should not worry about it. That means its energy in is equal to energy going out. So let us see how we can apply this. So what are the various energies? First of all, let us think. See, this is one of the energies, heat energy, which is entering into the control volume. This is the work energy. This is which is leaving the control volume. Then this is the internal energy of the fluid, which the fluid will take along with it into the control volume. Similarly, this is the velocity of the fluid. So that means there must be some kinetic energy of the fluid which is going into the control volume, then its elevation with respect to the datum is Zi. So that means there has to be certain potential energy of the fluid which is going into the control volume. And similarly, when the fluid which enters into the control volume has to do certain amount of the work while it enters into the control volume, and this work is actually known as flow work. And you know that flow work is given by product of pressure into volume. So this also has to be taken into consideration. Similar way, there are properties which are or the energy which is leaving the control volume. This is the internal energy, then this is the kinetic energy, and then we can take the product of the pressure and the volume, which will be the flow work leaving the control volume, and then we have the potential energy. So this is how we are going to take all sorts of the energies. So uh, so that means, first of all, when now, what is this first law of thermodynamics known for a control volume? It is actually known as steady flow energy equation. Okay, so steady flow energy equation represents the first law of thermodynamics application to the control volume or an open system. So, so let us see steady flow energy equation or the first law of thermodynamics, also called as SFEE. So, steady flow energy equation. This is steady flow energy equation. And what we are assuming? We are assuming steady flow. That means the mass which is entering into the control volume is equal to the mass which is going out. And we are considering that it is equal to m dot. And here once again I have shown the diagram which I showed you in the last slide also. Now, energy entering into the control volume is equal to energy leaving the control volume. This is the first law of thermodynamics, and this we studied in case of closed system also. So now let us see what are the various energies which are entering into the control volume. So first I have considered the mass which is entering in, and along with this mass we have the internal energy Ui which is going into the control volume. Then this is the flow work which is entering into the control volume. Then half Vi square, when multiplied by this mass it becomes kinetic energy. And then this is the potential energy term Gzi, plus we have QCV. You can see it, QCV is entering into the control volume. So this is taken on the left hand side, that is energy entering the control volume. Similarly, now we have to think about the energies which are leaving the control volume. So once again, similar equation we will write ME, this is the mass which is leaving, then this is the internal energy, this is the flow work which is leaving the control volume, and then we have the kinetic energy term of the fluid, then this is the potential energy term, and along with it we have the work which is also leaving the control volume, which is control volume, which is shown here by W dot CV term. So basically it is nothing but what we have considered. We have considered mass term multiplied by internal energy plus flow work plus kinetic energy plus potential energy. This is what we have considered, plus QCV, and that is equal to m dot E, once again internal energy plus flow work plus kinetic energy plus potential energy plus WCV. So this is a very simple way. We just have to see what are the energies which are entering into the control volume and what are the energies which are leaving the control volume. And this is the easiest way to write a steady flow energy equation. So let us proceed further. So once again, uh, now you know that H is equal to U plus PV. What is H? H is the specific enthalpy. And if you will see here, we have this product. We have UI PI VI, UI plus PI VI, and this term, this total term is actually enthalpy. So this stands for HI. So what we can do is, here we can write MI dot, so U plus PI. This is actually UI plus PI VI. So we have written UI plus PI Vi as Hi, which is specific enthalpy of the fluid which is entering into the control volume. Plus, this is the kinetic energy term. This is the potential energy term. Here it is the heat entering into the control volume, and that is equal to mass flow rate at the exit. This is the enthalpy of the fluid at the exit. This is kinetic energy, this is potential energy, this is work done. So this is how we can write the static flow energy equation. Then we also know that the mass flow rate which is entering is equal to the mass flow rate which is leaving. So then we can rearrange the various terms considering mi is equal to me is equal to m dot. And you can see uh, the first term which I am considering is QCV. This is the first term. So this is the first term, and this is the second term. And when it is taken on the left hand side, it becomes, there is a minus sign now, and equal to, now I am taking all other uh, terms which were present on the left hand side towards the right hand side. So the right hand side, the first term is this one, 3, and this is, let us say, 4. So here we get He minus Hi. Similarly, if this is 5, then this is 6, so it is 5, and this is 6. So V square minus Vi square divided by 2, and a similar manner we get the term Mgze minus Zi. So this is the equation that we get. And if we divide by mass flow rate on both the sides, then we get He minus Hi plus half V square minus Vi square plus Gze minus Zi. And finally, we can say that this term is now QCV minus WCV, He minus Hi plus half V square minus Vi square plus GZD minus Zi. Now, what is the unit of QCV actually? QCV, if I write, the unit is kilojoules per second. Okay. And when I divide it by m dot, what is m dot? It is kg per second. So when I divide both the terms, this second and second cancels out, and we are left with kilojoules per kg. Okay, and this is nothing but this is the value of qcv. So qcv has a unit which is equal to kilojoules per kg. And similarly, same thing will happen in case of wcv. wc is equal to wcv divided by m dot, and its unit will also be kilojoules per kg. And similarly, we can also find the units for the other terms on the right hand side. If I want to write this equation in the differential form, then I can write it as delta q minus delta w is equal to dh plus dke plus dpe, where dh is the change in enthalpy, dk is the differential of the kinetic energy, and here we have the differential of the potential energy. Or we can also write it as delta q minus delta w is equal to dh. Now kinetic energy, as you know, is given by half v square. So if I will I will take this term v dv, then it represents the derivative of kinetic energy, because if you take d of half v square, then it will come out to be 2v divided by 2 into dv. So it is equal to v dv. So it is equal to v dv plus g dz, because the potential energy is given mgz. So m and g is constant, so m derivative of potential energy will be given by mg dz. Or I can write this other terms remaining the same. I can write the kinetic energy terms like in this manner also, derivative of v square by 2 plus g dz. So this is how we will write this static flow energy equation in the differential form. Now there is one important thing that I would like to tell you is delta w. This work is actually the delta ws, that is the shaft work. So in an open system, we will always get work when there is a shaft in the system. If there is no shaft, we will not get the work. So what is a shaft? You should know what is a shaft. This is the diagram of the shaft. Okay, you must be studying in the engineering drawing or the graphics course. This is the axis of the shaft. Okay, this is the axis of the shaft. Now, what is shaft? Shaft is a cylindrical part or component of an open system which rotates about its own axis, rotates about its own axis. So here what we have done, here I have rewritten this particular equation. Okay, So it is equal to delta Q minus delta Ws. So delta W is now replaced by delta Ws dH plus dKe plus dPe, and it is also equal to dH plus d derivative of V square by 2 plus G dz. So let us proceed further. Now what we can do is we can apply this steady flow energy equation to a nozzle, but we should know what is a nozzle actually. Okay, so what is a nozzle? Nozzle is a device whose function is to increase the velocity of fluid, that is kinetic energy of the fluid, at the expense of drop in pressure, at the expense of drop in pressure. So what is the meaning of it? So let us try to understand. First of all, you can see the symbol of the nozzle. This is the symbol of the nozzle. How we have drawn it? We have drawn it like this. This is the symbol of the nozzle. Then we have made some sort of hatching here to represent that this nozzle is actually insulated. So it is an insulated nozzle, and the process that is taking in this particular case is reversible adiabatic. So that means the flow of the fluid is reversible adiabatic. Once it is adiabatic, there is no heat transfer. Q is equal to 0. That means QCV is equal to 0. And then let us see what are the other things that we can consider for this particular case. The mass flow rate of the fluid is m dot I at the inlet, m dot E at the exit. But as you know, this is a steady flow energy equation, so this value is equal to m dot. So that is a constant flow rate from inlet to the exit. This is the velocity of the fluid at the inlet. This is the enthalpy of the fluid at the inlet. This is the pressure of the fluid at the inlet, and this is the temperature of the fluid at the inlet. And simultaneously, we have these values at the exit also. Okay, and the fluid is entering here. So this nozzle you can say is circular in cross section. This is a circular cross section. If you will see it from the side view, you will see that it will look like something like this. Okay, so this shows the insulation part. Okay, and this is the inside diameter. So basically its cross section is circular. If you will cut it anywhere, so side view you can see a circle actually. Okay, now what is actually happening, why its velocity is increasing actually in this particular case? You can see, if I say the initial velocity is 5 meter per second, initial velocity is 5 meter per second, so the velocity VE will be greater than 5 meter per second. So that is basically we are increasing the velocity of the fluid from inlet to the exit actually. Now why this velocity increases? This velocity increases because there is pressure which is dropping actually. So pressure at the exit is actually pressure at the inlet. So what is pressure actually? Pressure is showing us a sort of energy of the fluid actually. So when this pressure will drop, that change in pressure will be responsible for the increase in the kinetic energy of the fluid. Okay. And one more thing, in case of nozzle, there is no shaft in it. So I will tell you in the next slide what is the meaning if there is no shaft actually. When there is no shaft, there is no work transfer in that particular case. I said you that if a shaft is there, then we can consider there is a work in that particular case in case of a open system. Otherwise, if there is no shaft, there won't be any work in the system. So there is no shaft in case of the nozzle. So first of all, what we can do is we can write the steady flow energy equation. Delta Q minus delta Ws is equal to dH plus dV square by 2 plus G dz. Delta Q is equal to 0 because control volume is insulated, and simultaneously we are also saying that the process is reversible adiabatic. Delta Ws is equal to 0 as there is no shaft. So delta Ws is equal to 0 in this particular case. Then what we can consider is this is the nozzle actually. This is the nozzle. Okay, if I consider that this nozzle is horizontal and this is some datum level, so you can see this value of elevation at inlet and this value of elevation at inlet, and this is at exit. They are equal actually. These are equal. Zi is equal to Ze. So what does it means? It means gravitational potential energy will be actually equal to 0, or we can also, if there is minor change in the elevation, we can neglect it. Okay, so that is what we have considered here, that we are neglecting this change in the potential energy. So what you will see, this delta cube is 0, no heat transfer, there is no work transfer, and the potential energy term we are considering to be 0. So we are left with two terms, this is, that is equal to dH plus dV square by 2 is equal to 0. So what we can do, we can integrate this equation from inlet to outlet. So we will get it as dH from inlet to exit and dV square by 2 from inlet to exit. So it should be not V, it is only V actually. It should not be VE or VI, and that is equal to 0. So then we get HE minus HI plus VE square by 2 minus VI square by 2 is equal to 0, or we can say V square is equal to under root of HI minus HE multiplied by 2 plus VI square the whole square. Okay, or I can say V is equal to this value under root of 2 HI minus HE plus VI square. So this is very simple. You can easily derive this equation from steady flow energy equation. Okay, now let us take a numerical problem on steady flow energy equation for nozzle. So what we are considering here is air at a temperature of 300 degrees Celsius. So we are given with a value of Ti which is equal to 300 degrees Celsius, and velocity at inlet is equal to 5 meter per second, and its temperature at exit from nozzle is 100 degrees Celsius. So T is equal to 100 degrees Celsius. Calculate the velocity of the nozzle at exit. So V is what we need to calculate. Take Cp for air as 1.005 kilojoules per kg Kelvin, and we can say that H is equal to Cp into T. Why H is equal to Cp into T? Because H is equal to U plus PV, and U is equal to CVT. H is equal to actually CPT plus, yeah, actually we need not to go from this equation. This equation will give us only Cp is equal to Cv plus R. So this is how we can get, but yes, in case of uh, gases, we can always use this relation that H is equal to Cp into T. Okay, so now once we are given with these values, okay, this is the equation that we have to use. V is equal to under root 2 Hi minus He plus Vi square under root. So we have the value of, that means I can always say that it is equal to 2 times Cp Ti minus Te plus Vi square. So it's quite simple, and you can easily calculate its value. So the options are given here. I have given four options. The first option is the final velocity VE is between 5 to 30 meter per second. Second option is it is between 30 to 150 meter per second. The third option is 150 to 800 meter per second. And the last option is greater than 800 meter per second. So I am not solving it. What you do, because you are listening to this lecture, you just freeze your screen for 5 minutes and calculate the value and just see what is your answer. Then in the end of the lecture, near the end of the lecture, I will tell you the correct answer actually. So try to solve it and see whether you write the answer, whether it is A, B, C or D. Write it in your notebook, and later on at the end of the lecture I will tell you what is the correct answer. You just try to see. If you have done any mistake, you will be able to understand. If not, then it's very good. So now let us uh, talk about diffuser. Now what is a diffuser? Now we want to apply the steady flow energy equation to this diffuser. Now basically diffuser is a device which is just opposite to that of nozzle. In case of nozzle, our function was to increase the velocity of the fluid at the expense of pressure, at the expense of drop in pressure. So in case of nozzle, when the pressure drops, its velocity increases. Whereas in case of diffuser, it is a component or device whose function is to increase the pressure of a fluid at the expense of decreasing velocity or kinetic energy. So what happens in case of diffuser? It is the pressure which is increases, or we can say the pressure at the exit is greater than pressure at inlet, and velocity of the fluid at exit will be velocity of the fluid at inlet, and its shape will also be that of opposite to that of a uh, nozzle. So this is the shape of a diffuser. So you can see it here. And once again we are considering it has an insulated boundary, so no chance of any heat transfer to the surrounding or from the surrounding to the control volume. I have not shown the control volume here, so you can show it by this dotted line. So this is the control surface of the control volume. Okay, and we are given with the, this is the inlet and this is the exit. So at inlet, the pressure is Pi, velocity is Vi, enthalpy is Hi, and the mass flow rate is Mi. Similarly, at exit, pressure is Pe, velocity Ve, enthalpy He, and finally Me is equal to Mi, which is equal to, we can say, M dot. And the process which is taking place is once again reversible adiabatic. That is why this value of QCV, heat transfer, is actually zero. And moreover, there is no shaft in case of a diffuser also, so in that particular case the delta ws value will also be zero. So this is the steady flow energy equation, same equation that we wrote earlier also. And now we can apply it. Delta q is equal to 0, delta w is equal to 0, so this term goes becomes 0, this term goes becomes 0. Then we can consider that the change in potential energy is negligible. So we can, rather than writing 0, we can say negligible. So once it is negligible, we are neglecting it, neglected. Okay, that is why we're neglecting it. Now, though here we are neglecting this particular value of the potential energy, but if in the problem the values of the elevation at inlet and outlet are given, then we must consider this value of the change in potential energy. Otherwise, you can neglect it. Now, assuming change in the potential energy to be negligible, we have dH plus dV square is equal to 0, or dH is equal to minus dV square by 2. So this is the equation. Once again, I have shown in this slide. So what I can do is I can integrate it from inlet to exit, integrate it from inlet to exit. So the left hand side becomes He minus Hi, the right hand side becomes Vi square minus V square by 2. And finally He is equal to Vi square minus V square divided by 2 plus Hi. And He can be written as UE plus PV. This remains the same kinetic energy of the fluid. So same purpose I have already told you. In case of a diffuser, the pressure at exit will be greater than pressure at inlet, whereas the velocity at exit will be less than velocity at inlet. So basically it is the drop in velocity which causes an increase in the pressure in case of the diffuser. Moreover, the area at inlet, this is AI and this is AE. So area at exit is more than area at inlet, whereas the reverse is true in case of a nozzle. But uh, there may be some nozzles where the area at inlet is less, whereas the area at exit is more. So please don't confuse in this terminology. Uh, that is not in your syllabus actually. Now we can apply this equation to the turbines also. What is a turbine? Turbine is a device used in a power plant for producing work or power. So in case of turbine, what is the function of turbine? Turbine is used for producing the power. So you can see in a turbine we have the shaft also. This is the shaft actually. Okay, this is the shaft of the turbine. So this shaft is actually the rotating part. It is basically used for producing the power actually. So the power is available at the shaft actually. So this is the inlet. The fluid is entering here at the inlet, and you can see this is the shape of the uh, turbine. Here you can say that it is very much similar to that of diffuser, but yes, there is a difference between the diagram of a diffuser and the turbine. that we have a shaft available here which is actually rotating. So this rotation of the shaft shows that we are available with the kinetic energy in the turbine. The pressure at inlet to the turbine is Pi, velocity, specific volume is Vi, enthalpy is Hi, temperature is Ti, velocity is Vi. And similarly, we have the various terms which are there at the exit of the turbine. One more thing, like other cases, process in a turbine is also a reversible adiabatic. Once it is a reversible adiabatic, QCV is equal to 0. So now what we can do is we can apply the steady flow energy equation, which is equal to delta Q minus delta Ws is equal to dH plus dKe plus dPe. So this is the steady flow energy equation. Now in case of turbine, once again we neglect certain things, whereas the other things need not to be neglected. So once again we have written shown the steady flow energy equation. So what we assume changes in kinetic energy and potential energy are negligible. So that will not cause any um, major difference in the value of the work that we obtain from the turbine. And this we will consider if nothing is mentioned about these things actually. If it is mentioned in the problem that the velocity at inlet is this much and the velocity at outlet is this much and the elevation at inlet is this much and elevation at the outlet is this much, then we cannot neglect these two terms. But mostly if it is not given, we have to neglect it. So if we neglect, what are the items we can remove? Delta Q is 0 because it is a reversible adiabatic process. Kinetic energy we are neglecting. Potential energy we are neglecting. So we are left with only two terms. Minus delta Ws is equal to dH. So here you can see minus delta Ws is equal to dH. So then we can integrate it between inlet and outlet. So finally what do we get? We get minus Ws is equal to He minus Hi. Or I can say that this is equal to Hi minus He. So this is the shaft bar which is equal to Hi minus He. So if I multiply both sides by mass flow rate, okay, I multiply this term by m dot and I also multiply here by m dot. This is what? This is the flow rate of the fluid. If it is a steam turbine, it is the flow rate of the steam. If it is a gas turbine, that it is the flow rate of the gas actually. So when I multiply both these terms, then this becomes the shaft power actually. Now this is actually shaft power, or the this shaft is a part of turbine. So this I can also call it as W of turbine. So W of turbine, the unit will be actually kilowatts. Kilowatt. You can see why, because if you take this term here, enthalpy has the units kilojoules per kg. So kg and kg cancels out and we are left with kilojoules per second, and kilojoules per second is nothing but kilowatts. Now let us talk about the application of the steady flow energy equation to a compressor. What is a compressor? Compressor is a device which is used for compressing the fluid, that is, it increases pressure and density, okay, as pressure increases and temperature also increases. So basically what is the function of a compressor? Function of a compressor is to increase the pressure and density of the fluid, but for increasing the pressure and the density we also have to supply certain amount of the work, and simultaneously when the pressure of the fluid will increase, its temperature will also increase. uh, So this is the diagram of a compressor. Now you can see this is the inlet and this is the exit. At exit you can see there is a smaller area because the fluid is compressed at the exit. So it should have a smaller area because the density has increased, the pressure has increased. The reverse was true in case of a turbine. You can see in case of turbine at inlet we have high pressure. In case of turbine, Pi is greater than Pe, and rotation of the we have written here also, we supply work to compress the fluid. So once again, it is insulated. We are considering process is reversible adiabatic. So this is the value of QCV. So QCV is equal to 0. We assume changes in kinetic and potential energy are negligible. We have considered it here, and then we can apply the static flow energy equation. Delta Q value is equal to 0. Kinetic energy term is also 0. Potential energy is 0. So we have dH and delta Ws terms, two terms only. So I can integrate this equation between inlet to exit, and I get minus Ws is equal to He minus Hi, or I can say Ws is equal to minus He minus Hi. And what does this negative sign shows here? Negative sign shows work is required to be done on the system, because in case of turbine we are supplying the work. So that is why this negative sign comes into the picture. Okay. In the next line, what I have written? I have written it as W compressor is equal to He minus Hi. Now I have removed this negative sign. I have removed this negative sign because now I know it is the compressor work, and compressor work is always negative work actually, because we are supplying this work into the compressor. And then if I multiply both sides by mass flow rate, here if I multiply by mass flow rate, and here also if I multiply by the mass flow rate, then this whole term becomes compressor power. So this W compressor is now compressor power required to run the compressor, and that is equal to m dot He minus Hi, and it has the units of kilowatts. So this is what I wanted to teach in this chapter to you. So that finishes my lecture here only. If you will have any doubt, you can ask me. And I told you that in the end of the lecture, I will tell you what is the correct answer for the velocity of the nozzle. So let us go back to the question of the nozzle. So the correct answer in this particular case is this one, C answer. It is 150 to 800. So just try to check why this is the correct answer. If you are unable to get the correct answer, then I will explain you it in the next class. You remind me in the next class that I have to tell you about this question. Otherwise, you can discuss about this in your group also, in your WhatsApp group, and understand why this value is coming out to be between 150 and 800. Actually, its value comes somewhere around 634 meter per second, if I am correct actually. So this is the correct answer. Okay. So hope this topic is clear to you. There are still some more concept left in this chapter that I will explain you in the next lecture.